Welcome to this year's annual refresher training for those working with X-rays. This training will also be used as part of the initial training requirements for new X-ray workers who are not licensed by the state of Nebraska in professions that involve X-ray use. Annual radiation safety refresher training is mandated by federal regulations as well as Nebraska Department of Health and Human Services regulations. Creighton University Radiation Safety has a webpage where you can find links to the state and federal regulations, Creighton policies, contact information, and forms. That address is www.creighton.edu/radiation-safety. X-rays were discovered in 1895 by Wilhelm Röntgen. Within a year, X-rays were being investigated and used in diagnostic medicine. Röntgen won the Nobel Prize for this discovery, but he donated the prize money to his university. He declined a title that would have gained him entry into German nobility, and he never patented his discovery, choosing instead to ensure that the world could freely benefit from his work. As radiation workers, we assume the risk of exposure to ionizing radiation. It is our responsibility to be educated with regard to the risk and with methods to minimize the exposures not only to ourselves but to others. Safe practices provide for the welfare of ourselves and to the public. First, let's review some of the definitions. So just what are X-rays? X-rays are a form of electromagnetic radiation. They are very high energy and have a very short wavelength. X-rays cannot be seen, heard, or felt. Machine produced, they carry enough energy to ionize atoms as they pass through materials. When working with X-rays, it is important to follow common safety practices as discussed later in this presentation. When speaking of radiation exposure, we are talking about the intensity of radiation in air. More significant to radiation workers are the units of absorbed dose and dose equivalent. The term absorbed dose refers to the energy deposited in material or human tissue as the radiation interacts with it. Dose equivalent is the equivalent biological damage from different types of radiation. The following slides will look at this in more detail. Exposure is the amount of charge liberated in air. It can be expressed in units of Roentgens or coulombs per kilogram of air. 1 Roentgen of X-rays will produce 2.58 times 10 to the minus 4th coulombs of positive or negative ionization in 1 kilogram of air. When radiation interacts with a person or with other materials, the ionizing effects result in an absorbed dose, measured in units of rads or grays. 1 gray is equal to 1 joule per kilogram, which is also equal to 100 rads. Different types of radiation, for example, alpha particles, can cause differing amounts of biological damage. In order to compare the different types of radiation, a quality factor has been determined for each. When you multiply the absorbed dose by the corresponding quality factor, which also is sometimes called a weighting factor, you determine the equivalent dose. An absorbed dose in grays will be converted to units of sieverts, and an absorbed dose in rads will be converted to rems using the quality factor. Grays and sieverts are the preferred international units. The units can be converted to rads or rems as shown in this slide. The guiding principle of radiation safety is ALARA, that is, to keep the radiation exposures as low as reasonably achievable. Creighton University's ALARA policy follows state and federal guidelines monitoring and evaluating occupational exposures of all radiation workers at regular intervals and making sure that no one exceeds regulatory limits. In some cases, area monitors may be placed to ensure members of the general public are not being exposed to radiation. The next topic is background radiation versus occupational radiation exposure. It is important to understand that we are all exposed to background radiation from natural and man-made sources every day. This can vary depending on factors such as soil composition, location, and altitude. However, Omaha's background radiation levels are close to the United States average of 360 millirems per year. As a rule of thumb, it may be easy to remember that this is about 1 millirem per day. Background radiation is not included in your occupational exposure limits. Only the radiation you received because of your employment is recorded in your dose history. Some examples of natural background sources are the foods we eat and cosmic and terrestrial sources. Radon gas is commonly recognized as a source of background radiation, contributing about half of the total annual exposure. Radon comes from the ground and can be present in some homes and buildings. Sometimes radon can also be present in well water. As for man-made sources of radiation, this group includes medical X-rays, building materials such as granite, and smoke detectors, just to name a few. Buildings like Grand Central Station in New York City have so much uranium-containing granite that workers could be subjected to as much as 120 millirems per year from exposed building materials. Occupational exposure is the radiation exposure you receive only because of employment-related tasks with radiation. Background radiation is not considered in your occupational exposure. Only the exposures that are a part of your job duties are recorded. Exposures you receive from your own medical care or from voluntary participation in research are also not part of your occupational exposure. The NRC has set radiation dose limits for occupational exposures. The whole body dose limit is 5,000 millirems per year, or in international units, that is 50 millisieverts per year. The limit for shallow dose extremities or skin is set at 50,000 millirems per year, or in international units, that is 500 millisieverts per year. The dose limit for the lens of the eye is 15,000 millirems per year, which is the same as 150 millisieverts. Pregnant workers who declare their pregnancy are limited to 500 millirems during the gestational period, or 5 millisieverts. Additionally, minors under the age of 19 are not allowed to receive more than 500 millirems per year from occupational sources. In 1905, two French scientists discovered that different tissue types had different radiation sensitivities. The more sensitive cells and tissues were those that were less mature, had high metabolic activity, and or were less differentiated. This explains the relative radiosensitivity of fetal cells and therefore the lower dose threshold for declared pregnant workers. In order for the lower dose limit to take effect for a pregnant worker, the individual must submit a declaration of pregnancy to the Radiation Safety Office. This letter is completely voluntary but required for the lower dose limits to apply. The declaration must be in writing and must be signed and dated. It may be submitted at any time during the pregnancy. A form for this notification can be found at the Radiation Safety website under the Forms tab. The dose to the fetus will be measured by wearing a second dosimeter on the abdomen under the lead apron if one is used. This table provides a summary of the various dose limits as specified in Nuclear Regulatory Commission and State of Nebraska regulations. Where do these dose limits originate? There is data available on health effects related to radiation exposure at high doses above 50 rem. This data includes survivors of the atomic bombs in Japan, the radium dial painters from the early 20th century, various industrial and medical exposures, and the uranium miners. Most studies have not been able to link an increased risk for cancer at lower radiation levels, that is, below 10 rem. However, most scientists agree that even low doses may slightly increase the risk of health effects, particularly cancer. There are several models proposed to explain the correlation between radiation dose and health effects. Some scientists believe there is a threshold below which there is no increase. Others believe the lower doses have a relatively greater risk. Some scientists even believe in hormesis, a theory that a small amount of radiation may actually be beneficial. However, the regulators have agreed that a conservative approach is the linear no-threshold model, extrapolating known data back to the lower radiation doses region. This model demonstrates that all radiation exposures, no matter how small, carry a proportional risk. How do we measure the occupational radiation exposure? We use dosimeters. Radiation workers may be required to wear a dosimeter to monitor their exposure. These badges do not provide any protection. They only measure the amount of radiation you are receiving. If you use a lead apron, the badge should be worn on the outside. The only exception is a fetal monitor, which is worn inside the lead apron. If you wear your regular dosimeter on the inside of the lead, there will be no way of accurately measuring your lens of the eye dose. Always wear your badge on the trunk of your body, somewhere between your neck and waist. Occasionally, a ring badge will be indicated for users working with fluoroscopy or in other areas where the radiation exposure to the hands may be expected to approach the ALARA limits. If you are issued a ring badge, wear it on your dominant hand. You can wear it on any finger. They can be ordered in 3 different sizes. Wear it on the finger where it is most comfortable and least likely to be lost. This diagram demonstrates the appropriate way to wear your badges. Whole body badges should be on the trunk of the body. If lead aprons are worn, make sure the dosimeter is outside of the apron. The ring can be on any finger but should be worn on the dominant hand. Creighton University issues dosimeters for 2-month periods, except for fetal monitors, which are exchanged on a monthly basis. The dosimeters contain reusable components which we do not have to pay for unless they are lost or more than 2 months late being returned. If lost or late, there will be a $14 charge billed to your department. Anytime you are curious about your dose record, you may request information from the Radiation Safety Office. If you need your exposure history in writing, a signed request is required. Any unusual readings or readings exceeding 300 millirems per wear period will be investigated by the Radiation Safety Office. An NRC Form 5 is provided annually detailing your previous year's occupational exposure. It is rare to see an annual exposure over 1 rem per year at Creighton University. At this level, occupational radiation exposure is statistically safer than many other common occupations or risks we encounter in our daily lives. In the following slides, we will review the biological effects of radiation. Radiation can damage cells either directly or indirectly. Of significant concern is damage to DNA. Ionizing radiation can break strands or bonds directly, or it can create free radicals by interacting with water molecules inside the cell, which results in chemical damage. When ionizing radiation strikes a water molecule, it can free an electron, creating free radicals. 90% of the damage to DNA is caused by indirect chemical effects of the free radicals formed through this interaction. DNA can suffer single-strand breaks or double-strand breaks. The final outcome for the cell depends on whether it can repair itself or if repairs are incomplete or incorrect. Most DNA will repair itself, and genetic integrity is restored with no lasting health risk. However, sometimes the damage is severe enough that the DNA does not repair to its original configuration. In that case, the cell often dies without dividing. However, there are times when the cell survives this change, and this can lead to health effects later in life. Remember that health effects are only discernible from naturally occurring health effects when whole body radiation doses exceed 10 rem at high dose rates. Occupational dose limits are set well below this threshold. Your occupational doses are monitored by the dosimeter you wear and reviewed by the Radiation Safety Office. Almost all radiation workers at Creighton University maintain their exposures below 1 rem per year, further minimizing any risk. Even at low doses, it is important to stay as safe as possible. This is integral to the ALARA policy, keeping doses as low as reasonably achievable. Here are a few strategies to employ. Time, distance, and shielding are the 3 main tenets of radiation protection. Understanding and using all 3 can help keep your radiation doses as low as reasonably achievable. First, let's discuss time. Always be aware of the time spent in an area where radiation may be present. Minimizing time while completing your task will keep your exposures as low as reasonably possible. Know the techniques for your radiation-emitting equipment and work efficiently to eliminate the need for retakes or multiple exposures. Second, use distance to your advantage. Radiation exposure follows the inverse square law, meaning if you can double your distance from the radiation source, your exposure will be 1/4 of what it was originally. Triple your distance and you now are receiving 1/9 of the original exposure. Finally, use any shielding that is available to you. Lead aprons are most common, and when working with fluoroscopy equipment, these aprons should always be used. There may also be portable shields, lead curtains on fluoro machines, leaded glass or walls, or even leaded gloves and goggles. Room shielding is used when there is a risk of exposing individuals in neighboring rooms. Finding the balance with time, distance, and shielding will minimize your exposure and therefore minimize your risk. When you use an X-ray generating machine, follow available technique charts and manufacturer instructions. Be very mindful of patient positioning to avoid the need for retakes. Digital imaging has had a positive effect on dosimetry by allowing images to be digitally enhanced and stored for later review. This results in fewer retakes. Always be aware of the machine you are using and the appropriate techniques to ensure the best results. There are procedural considerations which also will minimize your exposure and that of your patient. When using radiographic machines, the technologist must remain inside the control booth during the exposure. For fluoroscopic procedures, wear a lead apron and use the lead curtains below the table. Make sure your patient understands all instructions before you start and that they are not wearing any items which may create artifacts in the image. For cabinet or closed X-ray systems, area monitors are provided to measure the exposure near the equipment. This allows us to not only know the operator's potential exposure, but also that of others who may be in the room when the machine is active. The interlocks must be checked at least every 6 months, and if they fail, the Radiation Safety Office must be notified immediately. A log of usage and interlock checks is a good procedure. It is important to note that all workers at Creighton University have a right to a safe work environment. Part of that right includes a responsibility to help keep Creighton a safe place. If you are aware of any violations, or if you even suspect that something might be a violation, you must report it to the Radiation Safety Office as soon as possible. Should you have any questions or concerns, the radiation safety staff is available to help. The telephone number is available on the Radiation Safety website or on the Notice to Workers posting in all areas where radiation is used. Additionally, both radiation safety staff members have their cell phone numbers listed on the voicemail message just in case you call when both are not at their desk. The office is physically located in the Chris 1 Byrne Tower, room 213.